The world of drug discovery is this incredibly high-stakes game. We're talking science, time, and literally billions of dollars on the line. And right now, AI is stepping up as the new star player. But what happens when that star player isn't quite sure what its next move should be?
So, we all have this huge question in the back of our minds, right? Can AI actually cure diseases? I mean, it's the ultimate promise of this technology, a future where these powerful algorithms help us finally crack the code of human health.
But the answer is, well, it's a bit more complicated. The truth is, it can, but there's a huge catch. Only if we can actually trust its answers. Because in medicine, a wrong answer that sounds confident, that can be absolutely disastrous. And that's the core challenge we're going to unpack in this explainer.
Okay, so here's our game plan. First, we'll look at the massive gamble AI is taking in drug discovery. Then, we'll dive into what it actually means for an AI to say, hey, I'm not so sure about this one. After that, we'll see a showdown between the old methods and a new challenger. Watch how a hybrid champion is born. And finally, wrap up with what all of this means for the future of medicine.
All right, first up, AI's drug discovery gamble. And the subtitle here really says it all. The high cost of being wrong.
Now, this quote from the source research really hits the nail on the head. It says, relying on these uncertain models can lead to costly experimental failures, resource misallocation, and erroneous conclusions. Just think about that for a second. We're not talking about an AI recommending the wrong movie on Netflix. We're talking about a multi-million-dollar, multi-year research project going completely down a dead end, all because the AI pointed it in the wrong direction. The stakes just couldn't be high. So, how do we fix this? That's what we're getting into next. This is where things get really interesting, when AI admits I'm unsure. It's all about teaching our AI models to have a little bit of humility, to know what they don't know.
And the key concept here is something called uncertainty quantification, or UQ for short. It's basically a way to get an AI to tell us not just what it thinks, but how confident it is in that thought. See, it's not enough for a model to be right, it's absolutely critical for it to know when it might be wrong. This is really the foundation for building trustworthy AI in science.
And it turns out there are two main flavors of this uncertainty. On one side, you've got what's called aleatoric uncertainty. The easiest way to think about this is just the random chaos of the universe. Like a coin flip, you can't predict it perfectly, no matter how much data you throw at it. But then, on the other side, you have epistemic uncertainty. This is all about the model's own lack of knowledge. It's like trying to forecast the weather in a desert with no weather stations. The crucial difference? This kind of uncertainty can be fixed with more data and better models.
Okay, so this brings us to the big showdown, the old guard versus the newcomer. This is really all about a fundamental trade-off, the one between how powerful these uncertainty measuring methods are and, well, how much they actually cost to run.
So let's meet the main players in the ring. First, you have deep ensembles. These are the reigning champs, the gold standard. Think of it like asking a committee of 100 different experts for their opinion. It's incredibly powerful, but as you can imagine, it's also incredibly slow and expensive. Then you've got MC dropout. It's a clever, faster trick, but its answers can sometimes be a little inconsistent. And finally, there's evidential learning. It's the new kid on the block, super fast, but it can get a little tripped up when it sees data that looks really different from what it's used to.
And hey, the numbers don't lie. The gold standard, that big committee of 100 models, is really, really good. Just look at these scores from the research. Its RMSE, which is basically its error rate, is super low. That's great. And its RRC-AUC, which is a fancy way of saying how useful is it for finding the best drug candidates, is excellent. So yeah, this is the benchmark to beat.
But, and this is a huge but, look at the cost. Just look at this chart. The price of that power is massive. To train that Ensemble 100 model takes over 111 GPU hours for a single run. Compare that to the others, it's an absolute beast. It's powerful, for sure, but that cost makes it totally out of reach for a lot of labs. So the question is there a better way?
Well, that's what this next part is all about. A hybrid champion is born. This is where the researchers got clever and decided to combine the best of both worlds.
And they created something they call EOE, which stands for an ensemble of evidential models. So instead of that huge, clunky committee of 100 pretty basic models, they built a small, lean, super smart committee of just 10 of those more advanced evidential models. It's a hybrid approach specifically designed to get you all the power without that crippling cost.
And check this out. The results are, well, they're kind of mind-blowing. This is the 1-2 punch. First, look at the error rate, the RMSE. The new EOE 10 model has the lowest error of them all. But even more important, it also gets the best score on uncertainty, that CRPS metric. That means it's not just more accurate, it's also better at knowing when it's not sure. It's not just as good as the gold standard. In the ways that really matter, it's actually better.
And right here, this is the knockout blow. Remember that insane training cost for the gold standard? Over 111 GPU hours? Well, the EOE 10 model achieves its superior performance using just under 9. That's more than 12 times cheaper. It's like getting a Formula One race car that somehow runs on the gas mileage of a tiny scooter. It's just a massive leap in efficiency.
So, let's bring it all home. What does this actually mean in the real world? This is what it's all about. Smarter AI, better medicine, and what this breakthrough means for our future.
That number, 12x, is so much more than just a number on a chart. It's a game changer. Making this kind of sophisticated, trustworthy AI over 12 times more efficient means it's not just a tool for giant corporations anymore. It makes cutting-edge science accessible to more labs, more researchers, more brilliant minds everywhere.
So, why is this such a big deal? Well, a few key reasons. First, these improvements aren't a lucky guess. They are statistically significant and robust. Second, when the researchers really put the pressure on, giving the models totally new kinds of data to look at, the EOE1 outperformed everybody, including the old champ. For scientists on the ground, this means fewer false positives, which means less time and money wasted chasing dead ends. It lets them focus their tight budgets on the drug candidates that have the best shot at actually working.
You know, there's a line in the study that just sums this all up perfectly. They say that even small gains in an AI's ability to measure its own doubt can, quote, improve hit enrichment among prioritized compounds and lower experimental costs. This isn't just some abstract academic exercise. This has a direct, real-world bottom-line impact on how quickly and cheaply we can discover life-saving medicines.
And that leaves us with this final, really fascinating question. For years, the biggest roadblock for using AI in these huge, high-stakes fields has been about trust. But this research isn't just about medicine. It's a blueprint for building more reliable AI for everything. Engineering safer buildings, creating more accurate climate models, you name it. So now that we are teaching AI to quantify its own doubt, to actually know what it doesn't know, what other monumental problems can we finally truly trust it to help us solve?